I will now begin to speak English. Okay, so I am going to talk about a subject probably most of you have never even heard of, maybe not even the name. Là, c'est pas, je suis pas encore le texte, mais ça va venir. Okay. I am in the algebraic geometry group at Orsay, but I do model theory. But model theory has many applications and many links with algebra in general, algebraic geometry, and lots of other subjects. Okay? But in spite of all these applications, it is not very well known. Okay? It depends on the country, but not many people know what model theory is. Okay, so the idea, so model theory is part of mathematical logic, but it is much more like algebra and algebraic geometry than classical mathematical logic. It does not work on questions about the foundations of mathematics. It is more like abstract algebraic geometry or abstract algebra. Okay. And as I said, it's not very well known. In spite, je vous cache pas le, c'est bon? In spite of many applications. Okay. So this, because you don't know anything about the subject, at least I suppose, I have to start from zero. So what I will do will, I hope, be very simple, but also very informal, okay? In order to give you a small idea by looking at a classical application of model theory, also quite an old one from the 1960s, to give you a little idea of what we do. Of course, this is old style model theory I'm going to talk about. Now we do things differently, we do more things, but okay. So, anyways, I will also try to nearly give a proof. Probably I won't have time, or at least to give the strategy of a proof of. So here's my example. Here's a theorem. So this theorem has the advantage, the statement is very simple. So let f be a polynomial map. Whoops, I'll get used to it. Yes. Let f be a polynomial map from Cn, so C is the field of complex numbers, into Cn. If f is injective, then f is surjective. And yes, this is a true theorem. Okay? And so what is important is that C is the field of complex numbers is important. That the n is the same is very important. And what does it mean that it's a polynomial? It means that f of x1, xn, the coordinates, each of the coordinates are polynomials over C. Okay, so that's what it means. So, some first remarks. As I said, of course, one needs an assumption, the fact that f goes from Cn to Cn, the fact that it is C and not any field, although it is true also for R, but with a different proof. I mean, I don't think we have a model theory proof for the fact that it works for R. And F polynomial is essential because there are examples, for example, of holomorphic maps which are injective and not surjective. Okay? So we need all the assumptions. Okay. So is it easy to prove? Well, not really. For n equals 1, yes. You do not even need injective because we know that in C, every non-constant polynomial has a root. Okay? So you take f of x, which is of degree at least 1, and any element a in C, and you want to find a b with f of b equals a, but the equation of x when a equals 0 has a solution. So that's fine. But if you start for n bigger than 2, and so on, it gets more complicated. Okay? But in fact, anyways, what the statement is a simplified version. The real theorem is f not from the whole of the affine space Cn, but from Vn to Vn, where V is an algebraic variety, or more generally a scheme of finite type. But the idea of the proof is exactly the same. So we do it in the simple case. Okay, so the proofs. Well, it was, I think, proved first for the reals around 1962. I think they also had a first proof for, but which worked only when it was really C, the whole of the space. Okay. I've lost my laser again. Do you have it? Can you see it? Where is it? Oh, yes. Then, around 1969, people got interested in the more general statement for a variety or a scheme. And there are two proofs at around the same time. A proof by Borel using serious algebraic geometry, and a proof by Axe using model theory, which, for a model theorist, is totally obvious. Okay. Well, of course, one needs to know a little model theory, but only very basic things. Okay. So this is what I'm going to try to explain. Of course, it won't look obvious to you if you don't know any model theory, but I will explain what the tools are. Okay. So how can we prove, if we're a model theorist, and we are a little lazy, how can we prove the theorem? Well, we would like to prove it only in the very easy cases. Look at the fields where it works, and then use a transfer theorem. Okay? So we don't have to work or do a lot of algebra. Okay? So for which fields is it obviously true? Well, finite fields. If K is a finite field or just a finite set, any map from Kn to Kn which is injective is also surjective just by counting. Okay, so that was easy. Okay, now from this, it's also going to be fairly easy, but the proof, what needs there a little proof, that it works then for locally finite fields. A field is locally finite if every finitely generated subfield is finite. So let's prove it. So we have this polynomial map from Kn to Kn, which is injective, and we have some element in Kn, and we want to prove that there is a B such that f of f of B is equal to A. Okay, so that's what we want to prove. So, well, we take the subfield of K, which is generated by the things we are interested in. So the AIs, which are the element A, and all the coefficients of the polynomials Fi, which are in the definition of F. Okay. So now look at F restricted to this K0. So F0, the restriction, which is at each coordinate, it's the restriction of the Fi. Okay. Because of the way we chose K0, oops. So F0 is a polynomial map over K0 because the coefficients have been put into K0. Okay. So it's polynomial. Of course, it remains injective. And because it is polynomial, when you apply it to an element in K0, it remains in K0. So we are exactly in the assumptions of case 1. We have K0, a finite field, a polynomial map, which is injective. So it is surjective by case 1. And as A was in K0n, there is some B such that A equals F0B, period. Okay, so this is also very simple. So why is this useful? Well, we cannot apply this to C, because C is a field of characteristic 0. And of course, no field of characteristic 0 can be locally finite, because of course, any subfield of C will contain Q. But C has characteristic 0, but the main thing that characterizes C is that it's algebraically closed. And some other important algebraically closed fields are locally finite, and we're going to use this. So here we need to do a little algebra. Not much, of course. I mean, this isn't magic. We're going to have to do a little algebra. Okay. So I'm just recalling some things that you probably already know, just in case. So recall that a field K is algebraically closed if every polynomial in one variable of degree bigger than 1 has a root in racine in K. So, of course, the field of reals is not algebraically closed, but C is algebraically closed. Now, algebraically closed fields are very useful because if K is a field, K always has an extension which is algebraically closed. And even better than that, there's a particularly interesting algebraically closed extension. If K is a field, there is a specific extension of K, K bar, which is both algebraically closed and algebraic over K. Okay? We call K bar an algebraic closure of K. It's not unique, but up to isomorphism, it is unique. Two algebraic closures of K are isomorphic over little k. Okay? So that's quite useful. Okay, now about C itself, we will use, in the proof I've chosen, we will use only one fact, that C is algebraically closed, and that every other algebraically closed field of characteristic 0, which has the same cardinality as C, is isomorphic to C. Okay. In fact, more generally, in any algebraically closed field, once you know the characteristic, the isomorphism type is given by the transcendence degree. And so once you pass countable, it's given by the cardinality. Okay? So I remind you that the cardinality of the complexes is the cardinality of the continuum, which is the same as the cardinality of the set of the power set of n, les sous-ensembles de n, which is the cardinality of R, and which is 2 to the lf naught. Okay? So now in characteristic P, we're going to use a little more, because this is where locally finite will come in. A little more, but it's not much. Okay. So now let Fp be the prime field in characters, the finite field in characters P, the prime field. Okay, so it's Z over PZ. Okay, and it's always denoted Fp. And we fix it's very small, it's finite, but it's allowed to have an algebraic closure. So let's denote its algebraic closure as Fp bar. So inside Fp bar, which is an algebraically closed field, we have Fp. And in Fp bar, this prime field Fp has one and only one extension of degree n, which we denote by Fp to the n, which is also, of course, of characteristic P, a finite field of cardinality P to the n. Okay? And it has only one extension, and the way these are embedded, la façon dont ils sont plongés in the big Fp bar, is that Fpn is inside or embedded in Fpm if and only if F divides n. So Fp bar is really the inductive limit of these small finite fields. So it's the union of the Fpn's, but they form a tree, and Fpn is inside Fpm if and only if n divides m. And this gives the whole of this. So, of course, every finite subset of Fp bar will have to be contained in one of the Fpn's. Okay? So, in particular, every finitely generated subfield is finite. So, Fp bar It's an algebraically closed field of characteristic P, and it is locally finite. Okay, so we know from what we did before that access theorem is true for all locally finite fields. So it is true in Fp bar for every prime P. So now comes the model theory. So far we've done what? A little algebra. Okay. So now we invoke classical model theory, and we conclude that it's also true for C, because it's true for all the Fp bars for when P varies along the trine. Why? Well, it is a particular case of a classical transfer theorem of model theory, a very classical one, which nearly says every property which is true in the algebraic closure of Fp for nearly all P, nearly all means all except a finite number, is also true of C. Well, of course not. Okay. Okay, of course not. Fp satisfies I'm not of characteristic 0 for every P, and C doesn't. Okay. And for every P, Fp bar is countable and C is not. Okay. So that's not what it says. You have to be more precise about which properties can be transferred. So here's a real theorem. Excusez-moi, mais here we go. Okay, so every property which can be expressed, and that's where that's the essence of classical model theory. Every property which can be expressed by a first-order formula in the language of rings, because we're talking about rings and fields, and which is true in the algebraic closure of Fp for all except finitely many prime P's, is also true in C. Okay, that is a proof theorem. Okay, and of course, in order to understand this, one would need to really know precisely what a first-order formula in the language of rings is. But I can tell you, being of characteristic 0 is not expressible by such a formula. So life is still coherent. Okay, we're not. Okay, so let me say that this is a very classical transfer theorem, which follows from two ingredients, and which we can do in any like first year, first level model theory course. It's very classical. So of course one needs to understand the definition of the first order formula in the language of ring. And this is the first fundamental concept in model theory. Model theory studies mathematical structures like rings, fields, groups, by studying their subsets, which can be defined by the adequate first-order formulas. First-order formulas in the right language, the one you're interested in. Okay. And once we understand this, which we won't do in details because this is very boring. So I will just give you some examples and you'll have to, it's a lot like formulas you're used to, but there are one or two traps which are really important, okay? And then, of course, which is even more boring, when we need to check that access theorem can be expressed, if we want to pass it, to transfer it, it needs to be expressed by one first-order formula, or at least by an infinite list of first-order formulas, okay? Right. And then the second ingredient, supposing you know what a formula is, then we need to prove the transfer principle, okay? And again, this is a direct consequence of the first essential theorem in model theory, which is called the Compactness Theorem. Okay. Or equivalently, and that's the way we're going to do it because it's more amusing and it's more easy to do, it's kind of equivalent. We are going to use the notion of a limit of structures, not just of sets, of structures in the sense of model theory, and those are given by ultraproductive structures. I've chosen to do this because ultraproducts of structures, that's a construction that is not only easy, pretty, but very useful. In fact, I think it should be taught in first year of, and it's useful not just in model theory, everywhere. Okay, and why will this help? Because we will see that the limit, or the ultra product of the FP bars, when P goes to infinity, it is C. Okay, so that's, and then of course we'll need to check that properties, first order properties, transfer to the limit. With, okay, so that's the idea. Okay. Yes, there are lots of other transfer principles I'm not going to talk about. A very classic one, every first order formula in the language of rings, which is true in one algebraically closed field, is true in all algebraically closed fields of the same characteristic. Okay. And this is often, although not very precisely, used in algebra or in algebraic geometry, sometimes under the name Lefschetz principle. And the idea is one says, well, to show some algebraic property in an algebraically closed field of characteristic 0, well, it suffices to show it for C, and then we know it. Okay. So, I mean, that's the same thing, except this is not very precise. So, but it's the same thing. We will not use this transfer, and strictly speaking, we will not use the compactness theorem because we'll go through ultra products. So we will concentrate on the transfer, but still, I need to give you very quickly a rough idea of what a formula is and what isn't a formula. So at the basis of model theory is the notion of an abstract mathematical structure. Okay, so we use it afterwards. We'll have particular cases of these structures, and mainly these can be applied to algebraic structures. I say mainly, not quite. So mainly it can be applied to rings, fields, groups, ordered sets, and combinatorial structures of some sort, graphs. So we study these structures by looking at their subsets, which can be defined by first order formulas, which are the solution of a first order formula, and those are the definable sets. So what is a structure? It's a non-empty set with some operations or relations that are adequate for studying the structure, of course. Here we will not define abstractly, just examples of what it says in certain classes. And the type of operations you choose gives you the language of the structure in which you construct the formulas. So for commutative rings, which are our main interest here, well, we take the basic ring operations. So the structure will be the set R together with a plus multiplication, which are maps from R cross R to R, a minus, which is from R to R, and two distinguished constants, 0 and 1. And the formulas we are going to build are going to be built from these basic things, which is really what we do in algebra anyways. Okay. For ordered rings, we would allow ourselves to use the order relation, which is a binary relation, so a subset of R cross R. If we're interested in the class of all groups, we'll just take structures of the form G, multiplication, the inverse, and the unit, or the one. Okay, ordered groups, we add an ordering. For graphs, a structure, it will be a set S, which will be the set of vertices, together with the binary relation which links to vertices. Okay, so that is the language for looking at graphs. And as I said before, the operations give you the language. Okay. So for rings R, a formula will be the kind of thing you think a formula should be, and the kind of things we write all the time. But there are some very important rules. So first, we have the very basic formulas, which are built from the basic operations. So things like, for f a polynomial, f of x1, xn equals 0. So that's a basic formula, okay? And then, a remark. F of degree 0 is possible here. So for a prime number, p, P equals 0 is an honest-to-God basic formula, except it has no variables. Okay? And this formula is true in the ring R if and only if R has characteristic P. Okay, so characteristic P for fixed P we can say by a formula. Okay, so we start from the basic formulas, and then we do, as we do in real-life mathematics, we can say one formula and another formula. So we have conjunctions of formulas, so that's the end, and we usually denote it like this. We can say one formula or another formula, okay? We can negate a formula. So here we could have the negation of P equals 0, which would be P different from 0. I mean, this is all very, okay. And then we can also, we of course add quantifiers. There exists for all, as we do all the time with the same rules, okay? The only thing is, when you want to do this in a very abstract setting, of course, the definitions become complicated, and you need to check all kinds of things about, I don't know, parentheses, the fact that you could switch variables, which you don't need to when you know what you're looking at, okay? Now, the two fundamental rules which make it model theory and which enables us to use things like compactness theorem and transfer things is first, this is first order logic. So all the variables represent elements of the structure. When you say for all x, or there exists x, it has to be an element. You cannot say for all big X subset of, you can't do this. This would be second order logic. And even more important, formulas are finitary. So only finitely many variables, and only a finite number of conjunctions, disjunctions, or quantifiers. Okay? And this is exactly why transfer principles work. Okay, so you can say, as we saw, that R has characteristic P. But you cannot say that R has characteristic 0 by one formula. Well, you can try, you won't be able to, and the compactness theorem, which I won't state, tells you you cannot. Okay? But you can say it with an infinite set of formulas, but an infinite set doesn't make one formula. Okay? So you find an infinite set of formulas, it's the P difference from 0 for every P, and such that R has characteristic 0 if and only if it satisfies all of these. Okay. So this looks stupid, but it's actually very important. Okay. So what can one say? One can say that R is a ring, R is a field, in the usual way that you would say it if you can see that it's an honest-to-God, a real formula. K is algebraically closed. You can say, but you need infinitely many formulas, because you cannot say for every polynomial, because that's not a for all x. Okay. So what you need to say is degree by degree. So for n, yes, for each n, you can say every unitary polynomial in one variable of degree n has a root, and it's this formula. Okay. And then, in order to say that K is algebraically closed, this means that all these formulas for every n are satisfied. Okay. And again, you can say, for example, that a set is finite of cardinality n, but you cannot say a set is infinite. Okay. With one sentence. You can with infinitely. Okay, no more. Well, yes, we should check that access theorem can be written in this language. We won't do it, because again, you cannot say for every polynomial map. So you fix an n and an m, and you say that every polynomial in n variables and of degree less than m, which is injective, is surjective. Okay, in the same way as for algebraic closure, except it's a little more tedious to write, but it works. Okay. So now we do the transfer principle and see why C is the limit of the FPs. Okay. So ultra products. Yes, so we'll use ultra products, and these are very useful. Okay. And in order to simplify the definitions, as we did with formulas, we are only going to consider ultraproducts of commutative rings. But the strength of the construction of ultraproducts is that it works for every abstract first-order structure. Okay. So first, we do a Cartesian product. So we take a family of commutative rings, and the Cartesian product of the AIs, I've written the actual definition, but you all know what it is. Okay. So an element of the Cartesian product will be a tuple. Mostly we'll be thinking of infinite set of indices. That's the, okay, so it will be, if I is infinite tuples, where each coordinate is in the corresponding AI. And we can define on this big product coordinate-wise addition and multiplication, the way it should be, okay? And so, easy to check that with this definition, this whole product is a commutative ring, where, of course, the 0 is the tuple that has zeros everywhere, and the 1 is the one that has ones everywhere, okay? So. Okay, so now if the AIs are actually fields, do we get a field? No. This is never a field if I has at least two elements, because you just take this element and this one, and when you multiply them, none of them is equal to 0. When you multiply, you get 0. To avoid this, because we want to get a field as a limit, we are going to want to identify 0 with all the tuples such that AI is 0 almost everywhere. And we are going to quotient by an ultrafilter. So, definition of an ultrafilter, which I'm sure some of you must have already seen, but I'm giving it very quickly. Okay. So we take I a non-empty set. An ultrafilter F on I is, you have to get your level right, it's a family of subsets of I. Okay. So an element of F is a subset of I. And with these properties, the whole set I is inside, the empty set is not inside. If X, Y are inside, then the intersection is. If X is in F and something is bigger than X, then it is also in F. And remark, something that satisfies 1, 2, and 3 is what is called a filter. And now if you satisfy 4, which means that for every subset of I, either X is in F or the complement of X is in F, then you are an ultrafilter. Yeah. Fact, they exist. Filters exist, that's easy. And every filter is contained in an ultrafilter. Of course, this uses John's lemma, but we do. I mean, in model theory, mostly, we use John's lemma and the axiom of choice. We're not worried about this. Okay. Okay. A very important example of a filter is if I is infinite, the Fréchet filter, which I've written with this strange F, which is the family of all cofinite subsets of I. So X is cofinite if I minus X is finite. So it's the family of, let's say, all the big subsets of I. Okay. And of course, there are ultrafilters which contain this Fréchet filter, because every filter is contained in okay, I've lost it again. And if F is an ultrafilter, we will say that F is non-principal if F contains the Fréchet filter. Okay, and that's the ultrafilters we're interested in, the ones that work well. Okay. Now, we want to, our ultrafilter is like a measure. Sets outside the ultrafilter are small, like measure 0, okay? And we want to identify things which nearly everywhere look the same. In order to do this, we define an equivalence relation on the product, which is denoted by this thing. And we will say that two elements in the product are equivalent if, when you look at all the coordinates where they're equal, the sets of coordinates where they're equal is big, so it's an element of the ultrafilter. Okay, this is an equivalence relation. And the meaning is A and B are almost everywhere equal. And now we are going to look at the quotient of PAI by the equivalence relations. And so the cosets, the elements of this will be a class representing all the tuples that are equal nearly everywhere. Okay. And we denote this traditionally by pi of AA over F, the filter, the ultrafilter. And this is called an ultraproduct of the AIs. Okay, of course, its properties depends on which ultrafilter you choose. The equivalence relation is compatible with addition and multiplication. You can check. So this is a commutative ring. And now, because we have identified lots of things to 0, if all the AIs are fields, this is also a field. And this could be checked by hand, but it is a specific case for one specific formula, the one that says I'm a field, from a general theorem, which is the one which we'll use for the transfer, and which, once you know what a formula is and what an ultraproduct is in fact very simple to prove. And it's, I write it Théorème de Wash, because this is pronounced wash, and I find it very difficult to say Wash's theorem. Okay, so Théorème de Wash, or Wash theorem, for the case of commutative rings. This is a general theorem about structures and things. So if we have a family of, in our case, commutative rings, and an ultrafilter on the set I, if phi of x1, xn is a formula, a first-order formula, okay, so you don't know what it is, but you have an idea, in the language of rings, and if you take elements in the ultraproduct, when do those elements, when are they solutions of the formula phi inside here? Well, exactly what we were aiming for, if and only if this formula is true nearly everywhere in the coordinates. So if the set of i's such that this holds in the adequate AI, it is big, so it's an element of the ultrafilter. Okay? So something given by a first-order formula is true in the ultraproduct if and only if it's true for the coordinates in almost all I. Okay? Yes, I've said that again. The real strength is that it's true not only for rings, but for everything. Okay, application to access theorem. So this is what it does to do a talk with a mask. Okay. Okay. So we want to do an ultraproduct of the FP bars. Okay. So for I, we are going to take the set of all primes. And we're going to choose any ultrafilter on I. So I is a countable set, by the way, of course. So we are going to take any ultrafilter on I, which is non-principal. Non-principal is important because if one took a principal ultrafilter, then in fact, the product of the AIs modded out by this F would just be isomorphic to one of those. There would be a specific I0 such that the whole thing is really isomorphic to this. So that's not what we want. Okay. And so, and of course, we know these exists because we know the Fresher filter exists, and we know the Fresher filter is contained in some ultrafilter. And so we know that we can find such a thing. And now we consider the ultraproduct of the FP bars. So this is the ultraproduct of all those algebraically closed fields, each of characteristic P. And so we denote it by K. So by the theorem of Wash, K is a field, because this can be said by a formula. This can also, of course, be checked. In this particular case of rings, this can be checked by hand, because in fact, doing this construction in the case of rings is the same as modding out by a maximal ideal. Okay, you have to prove, so you can also look at it very algebraically, but at some point, for complicated things, you will need to know that you can transfer formulas. Because if you start to do it by hand for access theorem, I suppose you will manage, but it's, what's the point? You have a tool there. Okay. So, what are the properties of K? Well, K is a field. It's algebraically closed, because every FP bar is algebraically closed, and we know that we cannot say algebraically closed with one formula, but we can say, for every degree n, the fact that every polynomial of degree n has a root. And as this will be true in every... in every FP bar, it will of course be true in K. Okay? And so for every n, so K will have a solution for every polynomial of degree n, so it's algebraically closed. Now, an interesting question. Don't forget, our aim is to say something about C, right? So, okay. What is the characteristic of this big field? Well, you could just think about it and say, what could it be? I mean, why would it be one P more than another? Okay, because given a P, there's actually only one field in the list which has characteristic P. So, more precisely, let P be any prime. For any Q bigger than P, F bar Q is not going, Q is a prime also, F bar Q is not going to be of characteristic P, so F bar Q will satisfy the formula P is not equal to 0. So for all F bars except the finite numbers, they will all satisfy P is different from 0. So by Wash, K also satisfies P different from 0. So, and this for every F prime P. So there's no choice, K has characteristic 0. Okay? And so K is an algebraically closed field of characteristic 0. Hi, we're getting quite close now to the result. And by Wash again, and the thing I told you and which we didn't check because it's boring, access theorem will be true in K because it is true in all the F bar Qs, because that's what we proved, because those are locally finite. Okay? And again, as for algebraically closed, access theorem is not one formula, but for each n degree and m number of variables, or the opposite, you can say that for f polynomial of degree m with n variables, if it's injective, it's surjective. And this will be true in all the FQ bars. So degree by degree, it will be true in K. Okay. So we now have an algebraically closed field of characteristic 0, which satisfies access theorem. Okay. At this point, we could invoke the transfer theorem I talked to you about, and I said we would not use, which said, so, but that's not what we're going to do, which says that for first order formulas, all algebraically closed fields of same characteristic satisfy the same formulas. So if we are willing to use this, we have finished. Okay, so we found one algebraically closed field of characteristic 0, which satisfies access theorem, so they all do. But we're going to, it's more amusing not to use it. Okay. What's the cardinality of K? Well, it's not completely obvious, because K is a product of the FP bars, which themselves, being the algebraic closure of finite field, are countable. But it is not countable, and this is and in fact it has cardinality continuum, 2 to the LF naught. Okay? And the proof is an interesting exercise, which is true for ultra products in general. An ultra product of by a non-principal ultra filter, so a non-trivial ultra product of countable sets, of infinite countable sets, has the cardinality continuum. The proof is amusing because once you've found the way to do it, it's very easy. But honestly, one has to have the right idea. But it's and even more amusing and more difficult to actually find directly. Not only this, okay, this is not so surprising, but if you take now the ultra product of the FPs, the finite fields, okay, which are much smaller. But the point is, as you grow along the P, the cardinality of the FPs also grows. So you have an ultra product of finite structures where the cardinality grows, it's not bounded. Then it is also true that the ultra product has cardinality continuum. So that's, and it's more or less the same proof, but a little more subtle here. Okay, so now you can see the end, I believe. K is an algebraically closed field of characteristic 0 and of cardinality continuum. So K is isomorphic to C. Okay. So K satisfies access theorem. So certainly, if it's isomorphic to C, then access theorem is also true in C. Okay. So again, as I said, it is cheating to say that this is an obvious proof, because one needs to be comfortable with first-order formulas. And, well, ultra products, it's very easy to get comfortable with, and lots of people are comfortable with them, not just model theorists. But one needs to be comfortable with what a structure is and what a first-order formula is. Okay, but again, this is the beginning of model theory. This is how you start in model theory, is you define what a structure is and you define what first-order formulas are. And one of the reasons why I certainly don't do it, I mean, even when I give a course, I hate doing it, is that mostly it seems when you explain it to people that this is just a bunch of trivialities. Of course it is, because what it does is just present an abstract version of what we do every day in mathematics. Okay. And so we have to define, in general, knowing that you have a certain number of operations, a certain number of relations and things, you have to define what is allowed as a formula or not. And in order to avoid, and you have to do it at some point, or someone has to do it for you, okay? And you have to deal with horrible things like, when are formulas equivalent? Can you switch variables? How many parentheses are you allowed? Of course, I mean, if you had to invent, if you discovered rings for the first time, and you had to really define and understand what the ring of polynomials is, you would, and how you can deal with polynomials, you would have to deal with all of this. Is P of X the same as P of Y or not? When? And if we're allowed formulas of the form P of X equals 0, what do we do with formulas of the form P of X equals Q of X? And things like this, okay? And is it the same to say that there exists X such that for all, or for all there exist? Things we don't, fortunately, have to reprove every time we're doing mathematics. So, but when you start model theory, the first thing you have to do is do this properly or convince yourself that someone has done it, and this has to be done. This is why definitions are not so, in general, are easy but a little boring. And then you get to this horrible point when you have to explain what it means for a formula to be true in a structure. And basically you say, well, you define it by induction on the construction of the formulas, but basically at each stage you say it's true if it's true. I mean, that's... Now, before I finish, I want to say something. One has to be very careful, because one advances like this and you have the impression it's just trivialities. And then you get to the compactness theorem. The compactness theorem is a thing that tells you that you can say that a set has cardinality n, but you cannot say that it is finite or that it is infinite, because this contradicts the compactness theorem, which basically says if I have an infinite set of first order statements, and each finite piece has a model, meaning if I can find a structure which satisfies a finite piece of it for every finite piece, then I can find a structure which satisfies all of them. Okay? And if you think of it in terms of topology, this is really the compactness theorem. And this can that can also be proved using ultraproducts. This is, I think, the nicest proof. You take all those finite structures that work for each finite piece, and you do an ultraproduct of these with astucieusement chosen ultrafilter. And then what you will get at the end will be a structure which satisfies the whole infinite list. Okay? And this is where one really starts to work. Okay, so that's the okay. And what else did I want to say? The other thing, the way I presented it, it looks well, it doesn't look like anything, but it looks, if one thinks, it looks very syntactic. Okay, I have defined formulas and things, but what one is really interested in are the sets defined by these formulas, the definable sets. Like in a field, we would be interested in the Zariski closed sets as our basic sets, the sets that are solutions to a finite number of polynomials. Okay, and then we would take intersections, unions, and then projections, complements, and so on. Okay. And what model theory is really about is about studying structures by looking at the family of definable sets and looking at their combinatorial properties. Okay, what can we say? What other structure can we define using those definable sets? And we have criterion to know that even in a non-algebraic structure, when can one actually define a group? When can one actually define a field? And things like this. And these are the results which in the past, it's not so recent, I'm very old, in the past 15 years, have had really quite striking applications to algebraic geometry. Okay, so what I told you is just a small way into it. Okay, and last thing, do I have 3 more minutes? Okay. C'est bon? Oui, oui. Non, je disais OK, ça n'était pas par désespoir en disant bon, non. There is one important thing in the background which makes all this coherent with what we do in mathematics. Here I have defined, let's say, formulas or statements, and we really know what it means for a formula or a statement to be true in a given structure. Okay. But in mathematics, how do we actually prove that a statement is true in a given structure? We give a proof. Okay. And in order for all of this to be coherent, and I always find it amazing that it actually works, there is another side which is very syntactic and which is sort of proof theory, which tells you, it defines what a formal proof is. So it gives rules which sort of very formally represent what we do when we do a proof. But except in most systems, if you do it by hand, in order to prove, I don't know, that 2x equals 4, it takes like 3 pages of formal statements, but it exists. And the important point is the so-called Completeness Theorem, which was proved originally by Gödel, and should not be confused with Gödel's Incompleteness Theorem, which is much more complicated but also different. And the Completeness Theorem says that all this is coherent. Like, if some statement is true in all algebraically closed fields, it means that there is a formal proof of this statement from the list of axioms that say that you are in an algebraically closed field. Okay? So it says that if something is true, it means that there's a proof. And that is the thing in the background that makes all of it work, even though when one is doing model theory, this is the background, we know it's there, but we're working with the semantics side. Okay? We very rarely have to invoke the completeness theorem. But if the completeness theorem did not exist, the whole thing would make no sense. Okay? Because it wouldn't be related to real life mathematics. And okay, I think that's all I want to say.
Any question?
Sorry, I have a very stupid question, and I would like to know where is the essential difference between the model theory and the category theory is that we use a lot of logic in model theory?
It's very different. Even though there are some relations. Let me say, I mean, of course there are some relations, and a lot of them, some results in model theory can, if you want and if you like categories, be restated in terms of categories. But I mean, this is also true for practically every kind of algebraic thing. I would say that there is something called categorical logic, but which I must say I know very little about. But this is quite different from actual working model theory. And I would say, at least that's what I think, but it's biased. I would say that although model theory is quite abstract, it's still one level of abstraction below category theory. I mean, we really like, as you see, we like things to be easy. Okay? And of course, when we look at definable sets, the point is not to look at a definable set in a given structure, but a definable set is defined by a formula, and we want to look at it in all the rings or in all the fields. So for those of you who know categories, really looking at a formula is like looking at a functor, okay, between whatever and the set of structures and things. But we know this, but mostly we don't use it, because in most cases it doesn't, for what we're doing, add anything. But of course it's there at the back. But it is quite different. Okay.
Yes, thank you. I don't have any questions about math part. I think it was more or less okay. But just general question. So, how many people in the world do understand all of that proof in full detail? This is, in other words, how big is the field?
Oh, well, there are two things. First,
Thank you.
I have given quite a few mini courses about this. If I had 4 hours, all of you would understand the whole proof. Because I mean, I could define what a formula is, and that is the only thing that is missing. I mean, to define properly what a formula is, okay, and what a structure is. And that takes 1 hour. And of course, I wouldn't do all the details of the parentheses and things. But I mean, you do a definition by induction, you know what it is, and then Walsh's theorem is just like this, okay? So that's the first thing. So, I mean, this is so basic that, I mean, there are some countries where people in undergraduate studies have logic courses, and they certainly do this, okay? And the other thing is, when it gets a little more complicated, the model theory community is, let's say it's small compared to some other subjects, but it is not very small. In France, it's mainly represented in 2 or 3 different places for historical reasons. But like in the United States, people are in small groups in all kinds of universities. And also, because model theory has applications to very different subjects, now there are people coming from other subjects who have had to understand and learn part of model theory in order to apply it. Okay? In particular, this you might meet in your studies. There's a part of model theory which is called O minimality, and which sort of studies abstractly the properties that are typical of the reals, okay? But in other structures, and this, from the model theory point of view, is not very difficult because one knows what structures we're working in, but has wonderful applications to analytic geometry, and also recently, as some of my colleagues in the algebraic geometry group know, to some really hardcore algebraic geometry questions. So, as you say, this is not very well known, but particularly in France, it's not very well known for historical reasons. Let's say that in the old days, Bourbaki didn't like logic. That's a mild way to put it. And in France, if Bourbaki didn't like something, but nowadays, Bourbaki likes model theory. Who? I don't know, probably. Yes. But you've still managed to become big. Yes. Well, I guess you have more obvious applications than us. But so now you have geometers, you have real geometers who really, although they are not active in model theory, who have had to learn about model theory in order, because it's applied everywhere. Most recently, combinatorists who work on graphs, extremal graphs or something. There have been very, very interesting applications. So when we have a meeting in model theory, it's quite exciting, but a little tiring, because very often, so we have the pure model theorists who develop the theory of model theory, and then we have people from algebraic geometry, we have people from real geometry, from geometric groups, from group theory, and from combinatorics. They all come together, and we have to try and pretend we understand all their talks. It's very, it's quite interesting, but it is a subject which exists also a lot through its ramifications, and yeah. And unfortunately, some years there's a course of introduction to mathematical logic in the first year of the master. I don't know if it's the case this year. When it takes place, it's during the second semester or the third something. Anyway, it's at the end. And usually here, there is no course in the second year in logic and model theory, but there are courses. There's a big program of M2 in mathematical logic in, what's the name of this university now? Paris. University of Paris, which used to be Paris Diderot, and then before that was Paris 7. So that's, yeah, it's...
Okay, so thanks a lot.